University of Rochester, and so he's an expert on MHD theory, computations, laser-driven laboratory plasma experiments. His field of expertise is studying fundamental centrifugal plasma processes with charged particle acceleration, magnetized turbulence, dynamo, and many other topics that are relevant to astrophysically ethical plasma, and also to fusion energy and thermal confinement fusion. So he's a professor at the Department of Physics and Astronomy at the University of Rochester, and he's received many prestigious awards. An APS John Dawson Award for Excellence in Plasma Physics Research in 2019, Early Career Award from DOE in 2021, and the Presidential Early Career Award for Scientists and Engineers in 2025. So today, they'll give us a talk titled The Flash Code, an open simulation tool set for magnetized high-energy density plasma physics and astrophysics. So Petros is kind of a steward of the Flash Code, which is you'll learn about it just in a few minutes. And let's welcome Petros.
Thank you so much for the introduction, and thank you so much for having me. It's been a fantastic visit and a very fun experience being here. I'll be sitting here primarily because there might be folks on Zoom to hear me, but I'll be looking over there. My name is Petros Tzeferacos. I'm the director of the Class Center for Computational Science at the University of Rochester. In today's talk, I thought it would be fun to talk about my two favorite things, which is essentially how we can do astrophysics on Earth using high power lasers, and how we can do pulse power experiments to study inertial confinement fusion, to study high energy density science, and sort of bring both together in the context of the Flash code. Flash is sort of like the tool/linchpin of what the Flash Center is doing. It is a multi-physics simulation code. It does essentially radiation hydrodynamics and magnetohydrodynamics with extended physics. And it has been around for now more than 25 years. This is a code that has, as a project, has persisted through the years and has evolved according to the needs of the applications that it has been applied to. In terms of numbers, it has more than 5,000 users worldwide. More than 1,300 papers have been published using the code, and it's publicly available on our website where you can go and grab it. The code has been applied from astrophysics to CFD to high energy density physics, and its continued development has been supported primarily by the National Nuclear Security Administration, Los Alamos National Laboratory, Lawrence Livermore National Lab, and the Laboratory for Laser Energetics. Now, the Flash code actually started out as a purely astrophysics code. It was so as many of you know, the United States has a stockpile of nuclear weapons, right? When we decided in the 90s to stop doing testing, it became readily apparent that we had to find a way to make sure that our nuclear warheads actually still work. And the way to make sure of that was to start developing simulation codes that are capable of simulating these weapons. Now, this is in the purview of the National Nuclear Security Administration. For their benefit and for our good luck, the National Nuclear Security Administration in the 90s decided to not only start this race to develop simulation codes that are capable of doing this type of modeling in order to ensure the security of our stockpile, but also fund academics that can work on projects that are similar to what the national labs are interested in, but of course not nuclear weapons. And therefore, they ended up starting this ASAP program. It was essentially an initiative to accelerate scientific computing in academia to be a partner and a peer for the national labs that are part of the defense program. One of those 5 early centers was us, the Flash Center for Computational Science. At the time, we were at the University of Chicago, and the application that we targeted was essentially the explosion of thermonuclear supernovae. So how can we measure the emission that will come out of a type 1a supernovae, and what are the processes by which these supernovae explode? So this was essentially the first decade of the Flash development was geared towards understanding this problem and applying essentially multi-physics solvers onto such a complex configuration like the one shown here. The outcome of that research was great. We had a number of huge splashes on the public literature, but we also had the opportunity to develop essentially a simulation code that we made publicly available to scientists around the world. Now, fast forward to 2010, the National Ignition was coming online. How many of you have heard of the National Ignition Facility? Okay, so the National Ignition Facility was essentially the next step of what we can do for the stockpile stewardship, right? Essentially, we had these simulation codes that are doing really cool high-energy density science. However, how do we know that they're right? We can no longer do testing. There's no underground testing. There is no way of actually verifying our codes. Let's create a facility in which we can generate conditions that are similar to what we might be interested in, where fusion is relevant, conditions that you would find essentially in these high-energy density plasmas, and in the process try to achieve ignition, right? So at that time, essentially the National Nuclear Security Administration came to us and said, well, you have a really nice astrophysics code. It would be very helpful if you could take it and turn it into a high-energy density physics code so people can use it to essentially design experiments for laser facilities like the NIF, like the Omega Laser Facility at the Laboratory for Laser Energetics, and therefore, very much like we did with simulation codes, have academics engage with these facilities in order to be able to essentially grow and strengthen the stockpile stewardship program and have peers in academia to do experiments in these facilities. This is how programs like the Discovery Science program started at the National Ignition Facility, which I've had the honor and pleasure to chair for many years. Okay, so the NSA came to us and said, we would like an HD code, please. That's what we did from 2010 until our first release at sometime in 2012. That's when I came to the US as well, and I started working on Flash. Before that, I was a theoretical astrophysicist at the University of Torino in Italy, working on astrophysics code. So in the past 12 years, essentially Flash has become the premier academic simulation tool for laser-driven HED around the world. And these are some of the laser facilities where I personally have had the opportunity as a theoretical astrophysicist to do experiments in. So for some reason, they allow me in experimental facilities as well. Okay, so this is the Flash Center as it stands today in terms of our team. It is a big team of computational physicists, of postdocs, of visiting scientists, of a number of graduate students. And what we do is still anchored in astrophysics in the sense that we primarily study astrophysical processes, not by modeling the phenomenology like we were doing with supernovae, rather by trying to apply Flash and high-performance computing systems to design laboratory astrophysics experiments. So the idea is I can generate conditions in the laboratory that can inform how the astrophysical process actually works. Think of it as trying to eke out the physics of astrophysics. Now, The FLAS Center was founded at the University of Chicago in 2020. I moved the center from the University of Chicago to the University of Rochester because that was more aligned with the type of science that we were doing. And when we moved there, we essentially were able to expand our research portfolio dramatically with the support of the National Nuclear Security Administration, the National Science Foundation, the Department of Energy, Fusion and Energy Sciences, ARPA-E, the Department of Defense. And we have been working essentially on multiple topics ranging from laboratory astrophysics, HD, numerical methods for high-performance computing, computational fluid dynamics, plasma astrophysics, as well as inertial confinement fusion and fusion energy. Now, we're theorists, right? We do simulations, so we need to partner with a number of academic partners to do our experiments, and also the national labs of the defense programs, the NRL. We also work with folks at CEA and Rutherford Appleton Laboratory in the UK, as well as partners in small businesses and industry like L3Harris, like MIFTY, like GA. So these are partners that we have in the private world as well. The most important thing that we do, though, is train the next generation of computational physicists to be able to develop write hydro codes, but also perform validated simulations. What does that mean? Essentially, what we're trying to do is to train our students, postdocs, and researchers not only to use a simulation tool, but also understand what it does and use it responsibly in order to be able to do as much as possible predictive simulations in the world of HD. Through the years, more than 100 graduate students and postdocs have been trained at the FLAS Center. In a very long period where essentially the access to graduate students was very limited in our previous department, I created this apprenticeship model where we would also bring students and researchers from peer research institutions and collaborators spend time at the FLAS Center for Computational Science with us for extended periods of time to learn about the code and then go back and propagate the knowledge. And all of this is to sort of create a very broad pipeline that sort of taps into different talent pools across the US, across the world. We have entered essentially in a research field where the knowledge of how to use high-performance computing and computational physics was rather limited, right? Because in the world of high-density science, typically folks that were doing experiments relied on colleagues in the national labs to do the modeling for them. So a big chunk of what we tried to do was essentially to engage with the community through workshops and tutorials in summer schools in order to train people how to use responsibly codes like Flash and develop accordingly the code's capabilities. Okay, so this is for the people that are interested in Flash. Flash is a very big code. It's 1.2 million lines of code that encompass a number of capabilities that we had to expand for high-density science. I will not bore you with the details, but essentially it has all of the capabilities that one would require to apply this code for laser-driven and pulse power-driven high-density science experiments, and has been experimentally validated to a degree that other codes have not. So essentially, through the years, we have spent a lot of time in making sure that the physics that we put inside the code actually correspond to the physics that we see in our experiments. This has actually filled a particular niche in the user base. Essentially, the lack of a publicly accessible tool like Flash was very apparent to the NSA and translated in an exponential growth of our user base to more than 5,000 people today. The types of equations that we solve, and I can show equations because I'm at Cornell, is essentially extended MHD with extra physics. What we are doing is we're solving still continuity, momentum, induction, plus a generalized Ohm's law and total energy, but we expand the system in order to account for rapid processes that occur in laser-driven experiments or pulse power-driven experiments. Namely, what we worry about is the equilibration timescales of electrons, ions, and radiation. So we need to have extra physics in order to account for different energetic population, different energies in the various populations, in order to properly also couple the energy of ions and electrons with heat exchange or thermal conduction or radiation transfer and so on. So a number of capabilities. We also have a laser. We also have a pulse power driver that allow us to essentially model ab initio a number of complicated experiments. All of this is done using adaptive mesh refinement. This is a technique that allows for targeted resolution in parts of the domain where interesting things happen. I will not spend too much time on this, but I will say that in the last few years, we have spent a significant amount of time developing the extended MHD capabilities of the code and incorporating essentially in our generalized Ohm's law all of Braginsky's terms, and therefore we have a good grasp on the extended MHD that is of interest in these fields. We have coupled this effort with up-to-date transport coefficients, anisotropic thermal conduction, and also support for equations of state and opacities for a number of materials that people can sort of hook into the code and model the particular configuration that they have in mind. Okay, so these are the two things that I want to touch upon in this talk. The first one is going to be laser-driven experiments that try to understand how astrophysical magnetized turbulence works and how processes like fluctuation dynamo or transport of charged particles can be informed by laser-driven experiments. The second one is going to be how we can use a code like Flash to model pulse power gas path Z-pinch experiments. This is work that we've been doing with the Center for Matter under extreme conditions. And we have essentially applied Flash onto experiments, on gas path Z-pinch experiments that have been carried out here at the Cobra pulse power driver. Okay, so the first one is essentially a collaboration that has to do with the University of Oxford. I was lucky enough when I came to the US to encounter a copaesano from Bologna named Gianluca Gregori at the University of Oxford. And we started working together on developing essentially this program to study magnetized turbulence, fluctuation dynamo, and cosmic ray transport and acceleration. The basic premise here is we're trying to understand what is the process by which cosmic magnetic fields come to have the magnitude that they have that we observe today. One common idea is a process like fluctuation dynamo is acting upon seed magnetic fields that were generated at very early times in the universe life. And these magnetic fields are amplified to the values that we see today. And then they mediate processes like the transport and acceleration of cosmic rays. They can result in anomalous transport of heat when you have essentially thermal conduction interacting with magnetic fields. And the properties of the turbulence itself play a significant role in determining the formation rate of stars, the efficiency of that process, as well as the stellar mass distribution that we encounter in the interstellar medium. Sort of like a little primer on what fluctuation dynamo is, because this is not something that people might know. The basic idea is, it started out from a theoretical prediction from the 50s. This is Sir Barchelor. Essentially, the idea is you have a magnetic field loop that you toss inside a turbulent field. That turbulent motion can essentially topologically transform that magnetic field loop, right? Essentially, you can imagine that you stretch it and you twist it and then you fold it, and then you end up with a magnetic field that has the same size in terms of the field loop. However, it has twice the magnetic field, right? So essentially you go from 1 to 2 just by topologically transforming it. So this type of topological transformation, you can imagine that you can do multiple times. Essentially, 1 goes to 2, 2 goes to 4, 4 to 8. So this is essentially an exponential amplification, right? The idea is I'm stealing kinetic energy from the fluctuations of the turbulence, and I'm storing it in tension in the magnetic field lines. I'm transforming kinetic energy into magnetic energy. Now, this was an old idea that was modeled in the 80s using numerical simulations and has been studied extensively in order to understand how it operates in different plasma conditions, and looking at things like what is the critical magnetic Reynolds number for this process to work. One of the things that we can easily understand from this picture of topological transformations is that for them to work, we need to have a good coupling between the magnetic field and the turbulence. So this means large magnetic Reynolds numbers, right? As soon as you reach a critical value, you can actually go into this dynamo regime. And that was essentially the hurdle that we had to overcome in order to be able to create such an experiment in the laboratory on Earth. This theory was developed in the 50s, has been in continuous development for the past 75 years. So simulations of that started in the 80s. Experiments were attempted for the first time in the late 90s, 2000. But actually getting to that regime where you are surpassing this critical magnetic Reynolds number for dynamo to operate is really hard to achieve. There are also other considerations regarding, which plasma regime you're operating in. Is it the small Prandtl number, large Prandtl number, supersonic, subsonic? So there's a lot of interesting physics to understand in a rather limited problem set. It was this problem that we chose as a first approach to take FLAS and apply it into the lab astro world. And essentially, we used FLAS to design laser experiments for the Omega laser facility to generate a magnetized turbulence that would have magnetic Reynolds numbers above the critical value. Now, this to occur essentially required an out-of-the-box type of approach in the design process, in which we constructed this Rube Goldberg device of a target, where you have essentially two target foils which you illuminate from the back using the Omega laser. And then that creates a pair of counter-propagating flows that are forced to go through a pair of grids, which we misalign. And then when the collision happens, these plasma plumes shear and create a hot turbulent region in the center with magnetic Reynolds numbers that are above the critical value. Essentially, we were able to leverage the fact that we can have a lot of energy in a very small volume in order to increase the energy density of the system. Now, simulations of dynamo have happened since the 80s, so this and $5 will get you a cup of coffee at Starbucks. What was the thing that really mattered was the experiment. So we took this complicated device, fielded it at Omega, and we were able to demonstrate using the suite of diagnostics that we have at Omega that fluctuation dynamo was operating, and also demonstrate the amplification of the magnetic field by a dynamo action. Here is an X-ray image of the interaction region, the Kolmogorov spectrum that we were able to recover from it. And these are proton radiographs, which you can think of as trying to take pictures of the magnetic field with a Polaroid that doesn't use photons, but rather protons. So what we do is we do an experiment on the side where we implode a capsule, and a sea of protons will stream through the interaction region. They will be captured on a film, and this is what you see. Right? So you can actually capture the fluctuations of the magnetic field, and we developed essentially a technique to be able to reconstruct the path-integrated magnetic field from these images that were able to showcase how much the magnetic field amplification was. Well, this was a big finding. This is the reason why we got the John Dawson Award back in 2019. But more importantly, we've actually created a concerted effort to start providing a new way of looking at magnetized turbulence in the context of astrophysics. that was not theory, not simulation, not observations, rather a set of experiments that we could do and try to answer unanswered questions on how these processes work. And we have applied this to understand the temporal evolution of the magnetic field and how it saturates at late times to the point where we can actually see the evolution with subsequent shots in our experiments. We've applied this at the National Ignition Facility to study how strong magnetized turbulence is suppressing thermal conduction, and we're able to demonstrate suppressions of factors of about 100, much more than what was expected and consistent with what is being observed in galaxy clusters. We've applied this to study charged particle acceleration in experiments that we carried out at the GSI facility in Germany, in Darmstadt, Germany, using essentially charged particles going through this interaction region and giving us essentially how much these particles are energized by the lower Hybrid drift instability. And we have been able to answer many questions. Two of the more recent efforts that we're about to publish that I wanted to highlight here are essentially the first attempt at, let me get rid of this, you can actually see this, first attempt to bracket this critical magnetic Reynolds number. Essentially, it's sort of an open question on, when does dynamo actually sets in? It really depends on who's running the simulation. And this effort essentially leverages the fact that once you are able to achieve dynamo in the center, if you wait a little bit, what happens is that, sorry, this is somewhat stuck. What happens is that at late times, the formations that you see here actually go away. So there is a process by which magnetized turbulence can also decay apart from just increase, right? In fact, when you measure the temperature evolution in turbulence that we generate in the lab, what we find is that the temperature a little bit after the initial amplification will ultimately drop through radiation losses or thermal conduction losses, just the expansion of the turbulent plasma. And we can expect at some point the magnetic Reynolds number to become below the critical value, right? And therefore have the field itself decay. Now, one of the diagnostics that we're using in order to measure the plasma properties of these turbulent plasmas is Thomson scattering. The idea here is you shoot a laser at your plasma. That interaction can scatter off light that you can collect at a given frequency, and that signal that you get from the Thomson scattering can inform what the plasma properties are. However, essentially, you're measuring the plasma properties in a perturbative fashion, right? Essentially, you're shooting a laser at it. So the outcome of that is that it can heat up the plasma. Provided that you have quick enough thermal conduction transport, you can actually heat up the plasma not only at the place where you're shooting the laser, but have it actually affect a larger region. So in principle, one could imagine that we can use Thomson scattering not just to measure the plasma, but also to reignite dynamo in the sense of taking the magnetic Reynolds number back to a supercritical condition. So we have essentially two ways of looking at the upper bound and the lower bound of this critical magnetic Reynolds number by looking at when the dynamo switches off and when does it turn back on when the Thomson scattering happens. And in fact, when looking at a A-B comparison between essentially proton radiographs that are taken shortly after the Thomson scattering is being used to measure the plasma properties, what we find is compared to the no Thomson scattering beam, essentially no extra heating after it's cooled off, we see that at early times when the temperatures are high already and the Thomson scattering would be interfacing with this region, we see the structures evolve as they were in both cases, right? And the magnetic fields are comparable in both cases. So things start to change after about 31 nanoseconds, which is essentially when we have already switched off dynamo and the magnetic field start decaying. And what we see is that there is a distinct difference between both the structures that we see and the strength of the magnetic field that we measure. So the presence of the beam is actually doing something. And what we were able to show is that, well, first we can measure the decay rate of the magnetic field and get a gamma for that rate. But also we can combine the information that we get from the decay and the premise of this essentially being reignited dynamo to bracket the magnetic Reynolds number necessary for dynamo action to operate, bringing it into the range of 40 to 200, which is about what theorists are expecting, which is a good thing to confirm. This analysis will appear in an upcoming paper that we're finalizing now, and will be discussed also at the APS, DPP, if you decide to go there. There is another nice development that we have been able to show. There was a set of experiments that we've done in the span of a few years, where we were able to show the first experimental demonstration of fluctuation dynamo in supersonic turbulence. Now, supersonic turbulence is actually really hard to excite dynamo in. At least that's what the simulations tell us. And this was sort of like a Goldilocks type of experiment where we were trying to fundamentally create something that would have a high enough temperature and therefore a high enough magnetic Reynolds number, but also a low enough temperature for the turbulent velocity to be larger than the sound speed, right? So as to be supersonic. So that took a lot of design effort and a number of simulations that were carried out using Flash. But essentially, we had a rather successful shot day this last summer in which we were able to show that the turbulence that we were able to generate resulted to be supersonic with Mach numbers slightly above unity. And we were able to also measure the magnetic field amplification and properties of the amplified magnetic field in supersonic dynamo. This is something that will also show up shortly and will be presented by Hannah Poole, our postdoc at the upcoming APS. Okay, so this covers the first part. So lots of astrophysics, right? You can still do a lot of astrophysics in the laboratory environment using these high power lasers. But what about pulse power? The Flash Center is part of the Center for Matter Under Extreme Conditions. This is a center of excellence funded by the National Nuclear Security Administration that studies essentially magnetized HED in extremes. So we're looking at plasma states that one can find in inertial fusion energy, inertial confinement fusion, and we look at two specific things: energy transport in these HED systems, as well as material properties. These are, of course, tied in joint efforts that sort of bring together the physics of materials in extreme conditions with how transport operates in these plasmas. We use this initiative to take Flash and turn it also into a pulse power simulation code. So essentially develop the necessary algorithms, the extended MHD and current drive in order to be able to model Z-pinch experiments using this code. The first thing that we did was use essentially experiments and simulations that had been done before at the CSAR pulsar. This is an LTD pulse power facility at the basement of UC San Diego's engineering school. Farhad Beg operates this facility, and we were able to essentially develop a circuit model and the necessary extended MHD capabilities to be able to model essentially imploding gas puff Z pinches. The first thing that we did was tried to reproduce past results. Folks had done modeling of such experiments. These are gas puffs with a single and double liners of some noble gases, either argon or xenon and things like that. And we were able to compare flash to the Hydra code, which is the Lawrence Livermore National Lab simulation code that was being used to model these types of Z-pinches. Now, for those in the know, Hydra is a very well-respected simulation tool that has been around for a long time. It is instrumental for the success that the National Ignition Facility had in achieving ignition. And we work closely with Marty Marinak and the folks at Hydra to make sure that we were able to do this comparison in a way that we would also not jeopardize the fact that Flash is an open code. The results were really good. We're able to reproduce essentially the MRTI growth rates that we were getting in the experiment, and the paper has been published on this just last year. This type of development that we were able to do with the National Security Administration actually opened up a number of opportunities for us to engage not only with the NSA laboratories, but also with private industry. So we have actually worked with a company called MIFTY to try and provide them with simulation capabilities to model their state Z-pinch idea of creating essentially a performant Z-pinch in 1 and 2 dimensions. This was a code-to-code comparison with Code Mach 2, and also a number of applications have been done for the experiments that they are running today. A big outcome of that partnership was an Infuse grant that we got that allowed us for the first time to actually take these Z-pinch capabilities and turn them into 3D simulations. Now, this is the very first aluminum liner implosion. It's essentially an aluminum wire that we're imploding in Z conditions. This is an ongoing effort for us to be able to grow essentially the user base of Flash in the Z-pinch world. And in that, we have found a great partner at Pacific Fusion. This is a startup that was able to bring together something like $900 million from private investors to develop essentially a new power plant where they would actually have their first pilot of pulse power commercial fusion. So the Flash Center is lucky enough to now be leading the thrust area 1 of the second version of CMAC, and I'm in charge of the energy transport and HD plasmas now, which has allowed us to really supercharge our development and have things like synthetic diagnostics developed for Z-pinches. So if you're interested in applying Flash for the beautiful experiments that are being done here at Cobra, we will have a number of synthetic diagnostics that you are actually applying every day in these experiments. Also, there has been already some work done in terms of the self-emission imaging, Thomson scattering, and therefore it is growing into a very usable tool for folks that are interested in pulse power. Beyond that, I wanted to showcase a few things that might be relevant for the research that folks are doing here. There is an ongoing effort in the Flash development now to take our code and make it into a hybrid code in the sense of treating the ions as particles and the electrons as a fluid. This opens up the weakly collisional plasma regime for modeling. There is an approach that we are taking that is taken from the astrophysics code Pegasus that uses essentially a predictor-corrector algorithm to do fundamentally a Boris pusher for the movement of the particles and a 2-temperature hydrosolver for the electrons. The approach that we decided to take was one that will bring the gyrokinetics and continuum kinetics simulation code Jekyll into the mix. So this is a simulation code that's being developed at PPPL. It is very popular in space physics. It's very popular in kinetic modeling. The idea here is we're going to be using a sort of like a library version of Jekyll to replace our Boris pusher and have the update of the ion population carried out by Jekyll, and then the moments computed from that distribution fed back into Flash. This is going to be presented by my postdoctoral scholar at APS TPP in collaboration with Jimmy, and we will be working on that for a while. Another new development is the introduction of strength, material strength. We want to be able to essentially model to a certain extent effects like spallation, breakage, and damage in our simulations. This is a combination essentially of hot and cold plasmas abutting themselves. This is the inclusion of an isotropic stress tensor, and it follows essentially what we have seen in other codes like Gorgon and Pisail. This will allow for a new set of experiments. Development has also been done in terms of figuring out how gas puffs are actually formed. This is a fluid dynamics problem. We're trying to understand the injection problem and the density distribution of gas puffs before they're imploded. So we're doing ab initio calculations of these multiple nozzle configurations that create these multi-liner gas puffs. And we are finding good results in terms of how things behave in the experiments, and also fluent calculations that have been done in the past. What we did find, though, is that the creation of these gas puffs is not as trivial as one might imagine. There is actually a lot of physics going on further back in the nozzle. What we did find was that one actually needs to capture in exquisite detail the rate with which the nozzle is being filled. And that required us to actually start modeling the poppet responsible for the injection of the gas into the channel, which results in a very non-uniform spatial distribution of the gas that is actually being injected for the Z-pinch. It is an extra level of accuracy that we're trying to explore and see how well we do, but it also is a nice test bed for moving solids in a code like Flash. The last thing that I wanted to bring up is the new effort that we've had for Z-pinch modeling to employ the generalized Lagrangian multiplier MHD method. So the GLM is a technique to do MHD that has been around since the early 2000s. It's a technique that I have worked on when I was doing my PhD back in Italy, that fundamentally couples your system of equations with the introduction of a new scalar, a psi, that is coupled with a 2x2 Riemann solve with a normal component of the magnetic field. If you work out the equations, you can actually demonstrate that this psi will be responsible for advecting and diffusing, very much like the telegraph equation, magnetic monopoles present in your system. So unlike the standard MHD that we're doing in Flash, which is a staggered MHD approach, this one is purely cell-centered, which makes the implementation much straightforward, faster, lower memory footprint, but also allows for more errors to be taken out of the domain, especially when you are starting coupling, when you start the coupling of the various multi-physics that might be introducing divergence errors. Now they can be taken away by this by the species scalar at the fastest allowable speed, which is the fast magnetosonic. So this new technique has been verified. It is working with our theoretical benchmark. This is the magnetized no problem that was developed by Sasha Velikovic. Has been applied in pulse power Z pinches in the gas bath world. These are actually models of experiments that we've done here at Cobra with folks at CMEC. People might recognize the current profile, and we are in the process of robustifying the implementation and putting it out for the users to use. So, in conclusion, I would like to say that the Flash code as a multiphysics simulation tool has been broadly accepted by the academic HD community, both in the US and abroad. This was made possible by the long-standing partnership that we have with the Laboratory for Laser Energetics and the Los Alamos National Laboratory. The applicability of the code in both pulse power and laser-driven experiments has allowed a number of folks to pursue numerical modeling alongside with their experiments, and therefore has allowed us to contribute to training the next generation of computational scientists. In terms of the advancements that we were able to make in magnetized turbulence and fluctuation dynamo, I would say we're just beginning. There are a number of questions that we still need to answer. We've been able to demonstrate dynamo in fluctuation dynamo action in different plasma regimes, understand some of its properties. We can answer many more questions that are open in the literature and keep working on those. For the pulse power modeling, I would say that this is a brand new world for us. It is a very complicated and an exciting world with a lot of fundamental MHD instabilities that students can sink their teeth in and codes can break. So we're excited to be part of this push and expand essentially Flash's application to this new partner space. With this, I will thank my sponsors and funding support, and I'll be glad to take any questions.
Okay, well, time for questions. Students first.
Yeah, so I have a question about the hybrid, like the hybrid model.
Yes.
So, I just want to know why you want to treat the electrons as the fluid and the ions as the particles, and why not the other way around?
Right, that's a good question. So the basic idea here is we want to be able to simulate experiments that are of a very large scale. Now there are different ways in the answers of equations that you can use to have a good representation of what you're trying to do, right? In the most coarse way, you can say, okay, I can do MHD, single fluid, everything ideal. Then you can go ahead and say, well, I care about the physics of things that happen at timescales relevant to the motions of the protons or the ions, right? These are not so far away from the MHD part, but are longer compared to the timescales of the electrons, which are very, very, very short. So when trying to model experiments that are happening in laser facilities like Omega or NIF, you need to make this sort of cost-benefit analysis to see what type of physics you want to be able to capture. So if you want to do an ab initio simulation in which you're shooting a laser at something and creating a flow, and then you have that flow interacting with a different plasma flow, that will require sort of like taking a step away from trying to resolve the very fast motions of the electrons. So it is essentially trying to get into a regime which is between hydro and PIC, particle and cell approach. And that in-between regime is this weakly coupled ions in our plasma. This is why we're targeting that, because we want to have larger scales than what you could do in PIC and get away with larger time steps to see a large scale, a long time evolution of your plasma experiment.
Yeah, like the kinetic treatment of the electrons that give you like like more result.
Yes, exactly. So essentially what we're trying to do, to understand is a plasma regime in which the electron physics can be ignored while the ion physics is sort of the important thing that you're looking at. The specific application that we have in mind for this line of development is the development of collisionless shocks. And these happen essentially via a process which is called the Weibull instability. It's a two-stream instability that develops at timescales defined by the ions, and we can sort of ignore the electrons that are there to create the return currents.
Well, one of the interesting questions in dynamo theory is not just whether you generate magnetic magnetic energy, but whether you generate at large scales. I'm wondering, have you looked at the spectrum of the magnetic fluctuation in addition to that?
Yes, absolutely. This is a great question. So extracting the magnetic power spectrum, the magnetic energy power spectrum in dynamo experiments is a bit tricky. The tricky part is that when you're doing these proton radiographs and you're reconstructing the magnetic field, then you have effects that have to do with a integration of it. So there is a path integration in the process, but you can sort of convince yourself that are specific areas in the plasma where you can say it's homogeneous isotropic and take advantage of that. Now, we have been able to construct power spectra. So we have seen the inertial range, what we think is the inertial range, go with power laws of k to going as 10 as e to the minus 1 to 1.5, so decay a little bit shallower than the Kolmogorov one. We have seen different power spectra depending on the compressibility of this. And the basic thing that we're trying to do with all of these experiments is sort of try to tie back to the simulations themselves, in the sense that we can do synthetic images of our simulations and compare directly with the experimental images, and then apply the same technique that we're using to recover the power spectrum from the experimental image to the synthetic one. And that allows us to sort of understand the various little differences that exist between the methods. So in short, yes, we can recover power spectra. We are limited in the range that we have because it's the size of the interaction region versus the pixel of our diagnostic, which is unfortunately not yet at 2-decade size. But there are still a number of questions to answer there, because one of the things that we're very interested right now to do is to study fundamentally how fluctuation dynamo at small scales interacts with large-scale dynamos. So we have a set of experiments lined up with simulations to back them, in which we're trying to create large-scale helical motion in our plasma with fluctuations present in it. So sort of see that interaction between small and large scales and how that changes the power spectrum. It is a fascinating field. I've been actually working a little bit also in driven turbulence applications and how they tie in with extended MHD as well. And I think there's so much more to get from this type of research. Thank you so much for the questions. Yes. There are some structures that we can. There is a particular design that was actually first developed at Imperial College. I remember a friend of mine, Alberto Marocchino, when I was doing my PhD, was working with Sergei Lebedev, and it's essentially a collision, an off-center collision of multiple flows that can generate a large-scale rotation. So you can imagine essentially the experiment that I showed replicated at 90 degrees, the target's tilted, and then you would have essentially an off-center collision that would provide a large-scale rotation. Now, with lasers like Omega, you can actually take that target and replicate it multiple times, now you can create a large-scale rotating turbulent plasma column, which is my next proposal.
Excellent. Say there's a student in this room who wants to start running Flash. What's the next steps?
So there is it's very easy. That's the first thing to understand. Using Flash is actually a very fun experience in the sense that it is one of the codes that you can actually go in and see everything. Now, how do you start using it? Well, the easiest thing to do is you go to our website, you click the Flash code, you click the download, the code request, you get the code. Then you can either read the 500-page textbook that we have, that is our user manual, or you can shoot me a message and I can give you a brief tutorial, sort of show you around, get you started. Also, because you're less than 2 hours away from Rochester, I would gladly have anyone, just show up at my office, knock on the door, and spend some time with us. So if you would like to learn more about Flash and your students would like to sort of get engaged, send them over. We'll have them over, just pay for their Airbnb or hotel for a few days, and then we can have them spend time with us, with our graduate students, and we'll show them around.
So I understand that most of this work is related to inertial kind of fusion, maybe Z pinches and so on. But in the 90s, there was a lot of enthusiasm about modeling full tokamak physics using gyrofluids and maybe even modeling the entire ether and so on. And then it kind of petered out. Is there anything that either prevents or will one day allow Flash to model the entire tokamak?
This is a good question. So what I would say is that the people doing gyrokinetics did a really good job, right? And now the codes are sort of set, and there's little expectation of surprises anymore. So it's more of an engineering problem rather than a scientific discovery problem.
Gyrofluids. I meant gyrofluids. Gyrokinetics, I don't think they can model the entire.
Oh, gyrofluids like in tokamak configuration, right?
Like in Borland's or.
Got it. So bravo. So this is not something that we plan on expanding into. I think there is enough simulation codes there to support efforts forever. However, there are some. There might be some application in space physics that would be interesting for us to consider. So we have worked in the past with folks like the developers of Petros from Michigan, and I think that there might be some opportunities in the future to seek funding from different avenues to look at these types of systems. But for now, all of my postdocs and researchers are gainfully employed, and my graduate students are graduating. So we'll keep the size that we are and not grow further.
Some people will be writing their codes on GPUs.
Uh-huh.
They think that you're planning Flash or.
So we're actually doing it already in the sense that so GPU computing is something that I'll date myself a little bit, but when I was doing my PhD back in 2010, the first versions of C for CUDA, that's how they called it back then, were coming out. And one of the things that we wanted to do with our astrophysics code, Pluto, was to it's named after after Mickey's dog, not the planet or the god. We couldn't show Pluto a lot because we would be sued by Disney. But what we looked at the time was how hard is it to rewrite essentially a full code into CUDA C And that was my postdoc. That was the first thing that I did after I finished my PhD. So I took Pluto and rewrote it in CUDA. I was able to get essentially perfect acceleration for the 80% of the compute load that I put in. I got a 5x speed up. So it worked really well back then, but it had the problem of supporting only single precision. And it was an API that was changing essentially every month. So at the time we said, okay, this doesn't make sense to sink too much investment in and wait a little bit to see what happens. Now we're in a world where GPU computing has evolved dramatically, right? And we're at a stage where I think that this old paradigm of having one person coding up a code in a particular way for, the set of applications that we're doing with Flash is too much of an effort. So the approach that we've taken for GPU acceleration is twofold. One is, first off, leverage the investments that the NSA has already made, and the Department of Energy as well. So the exascale computing project has funded Livermore to accelerate onto GPUs the Hyper library, which is essentially a sparse linear algebra solver that the good folks at CASC are developing. Now that runs on GPUs. It has some acceleration. We have an API for it, and we're using it all the time for our implicit solves. So we're effectively running on GPUs already, and we are seeing acceleration in particular architectures, but it's not across the board. Now that's one. The other approach, which is the more future-proof approach, is to take Flash and rewrite it in a code like in a language like C++. That allows for interfacing with AMR libraries that exist out there that already have a layer to interfaces like Cocos or essentially think of infrastructure that exists that is being funded by the national labs, that it will be there for a while. We'll see. I mean, my approach has been to sort of try to bring in the perfect people that want to do this. This is not a project that one can do, in the time span of a postdoc. It would be a horrible postdoc work, actually, because you wouldn't be able to publish much while you're just rewriting code. One approach that we have been looking into is actually the use of large language models to do code transformation. We have discussed this with certain players in that world. I'm not allowed to NDAs. I'm not allowed to divulge too much, but this is something that I think has legs, and it might be an easy way to avoid essentially someone spending so much time to rewrite a code like Flash, which is, as I said, more than 1 million lines.
Yeah, since you're on this slide, I'm a little familiar with Jekyll, so I can't remember how to spell it. It's fairly expansive bit of credit in its own right, but it's pretty interesting for us for studying feasibilities. So, but it's you said something kind of cryptic. You said you're using a library version of Jekyll.
So yes, this is something that Jimmy has been working on. They're trying to sort of standardize the API of Jekyll as it can be seen, so you can precompile Jekyll and have it read on the fly by another piece of code that will be accessing its functions. So the idea is, so Jekyll already has a fluid code inside it. So what we have been doing is essentially we have been prototyping the bridge to Flash with the internal version of Hydro in Jekyll. And right now we are at a point where we're happy with what we're getting, which is great. Jimmy has actually worked on a spectacular new algorithm that uses essentially a frame of reference that goes with the fluid. So you can imagine as a kinetic correction of the fluid properties that Flash computes already. coming from the moments calculated by Jekyll. So that's going to be the approach. Now, we do want to have essentially the Flask users that are going to be using this not have to worry too much about Jekyll. So the approach will be one where it is essentially sort of hidden from sight for our users, but of course available for people to look at.
I have a question about this, your intention to swap out peak treatment with, with a loss of treatment. So in the past, people have tried to do that, but usually would get stuck at a small number of dimensions.
Yeah.
So, big codes, they're very noisy, but they're very fast. But, these sorts of loss of codes, they're much cleaner, but they're very slow. Are you sure that, you're gonna make that important number of 3 for the number of dimensions?
This is a very good point. So we have been racking our brains to figure out how to do this in a way that it will not essentially tank our time step, right? Because in general, a hydro solve is much faster than one of these glass of Maxwell solvers, right? The trickery that we'll try to do is because unlike PIC, where you essentially are moving things around on a separate way from the fluids, we can be solving essentially Jekyll on the same grid structures that we have in our block-based AMR. So the idea is the following: you can have the spatial domain that Jekyll is attacking be essentially a de-resolved region of our AMR. So think of a child block being de-resolved 1 or 2 levels, maintaining the well-nestedness of that grid, and then at that level, so lower resolution, but the same dimensionality as the original run, being the place where we're actually doing the kinetic solve. Now, you're absolutely right. We're not going to do 3D 3V. That's nuts. It's just too expensive. So for now, what we're looking at is essentially 2D 2V at the lower resolution, which we have convinced ourselves that is doable and sort of like 2 times more expensive than what we already do in the hydrosol for the particular application that we have in mind, because that is going to be our starting point. Now, if this has legs and we find a way to do this better and faster, then we might expand it to more dimensionalities and different configurations in phase space. But for now, this is more of like, let's see if we can do it. And it's going to be a very nice applied math. It's going to be a JCP paper, most likely, rather than a physics of plasmas.
Oh, no more questions. That's St. Petros, but it's not a problem.
Thank you all. It was a pleasure.
So our next development will be